Hey class, welcome back. Today we're going to be going to Module 5, Numbering Systems. Specifically, we're going to be talking about two specific numbering systems that include the binary and hexadecimal. These two numbering systems are really important because it has a lot to do with addressing, specifically when it comes to networking. So for example, when it comes to IPv4 addressing, we use binary. When it comes to IPv6, we use hexadecimal. When it comes to MAC addresses, we use hexadecimal. Now we're going to talk about the differences between the two and when we would use it. So we'll go ahead and start things off. But that's pretty much a quick, brief. Those are the main use cases we're going to be talking about specifically for this class. Now in binary, something that we need to make sure we remember is binary, bi meaning two. Data is going to be represented in either a 0 or a 1, an on or an off, right? Hexadecimal, on the other hand, it's every bit or every number, to say the least, is going to be represented one of 16 characters. It's 0 through 9, A through F, meaning to represent one bit, it's going to either be a 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, A, B, C, D, E, or E, F. Sorry. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F, 16. All right, so in hexadecimal, to represent one bit, it's going to be one of those 16 characters. All right. So we'll go ahead and scroll through and discuss the numbering systems and the importance of being able to convert from one numbering system to another. The other numbering system that we use in our daily lives on a regular basis is just a decimal system. That's like the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, like 11, 12, 13, 14, we'll use right now. Usually when it comes to addressing, we convert binary into decimal. So for example, an IPv4 address contains 32 bits or 32 zeros and ones. For our sanity, we put that into decimal. So rather than 32 zeros and ones, we'll have 4 octets. So it'll be like 192.168.0.1, right? When we're talking about numbers like that, it's more, they're referred to as decimal, right? They're whole numbers, right? Well, all of them are whole numbers, to say the least, but we'll go ahead and jump into this real quick. So we'll start off with the binary. So binary essentially, like I mentioned before, is a series of ones and zeros. IPv4 addresses have 32 zeros and ones. They're broken into every 8 0 or ones is considered an octet. So technically, every IP address is 4 octets. Octet meaning 8. So every 8 bits, it's an octet. So it's split into 4 sections. So a 32-bit, so if you think about 32 divided by 8, that would be 4, right? So 4 octets. Or 4 times 8 is 32 because there's 4 octets and 8 bits in each octet, right? So 32 bits. Okay. Now, usually in binary, it's zeros and ones, but when we want to convert it into a decimal format, we change it to, for example, if we're talking about this specific string of 32 bits, this converts into a dot decimal of 209.165.200.225. So you can see here, the decimal is just for sanity's sake, we can definitely be able to express it and be able to notate it a lot simpler rather than a bunch of zeros and ones, because we read this, we immediately know what 209 is. But the thing is, computers and technology only reads zeros and ones, right? And so they're going to see, the computer's going to see this string of numbers while we see this. Okay. So one thing that's really important is that we have to know how to convert from this 32-bit number into this decimal number. And that comes into play especially when you're subnetting. Subnetting is really important for this class because you have an IP range, right? You have like thousands of IP addresses. And you want to be able to segment them into specific zones or specific mini networks to put specific people into each of those networks. Otherwise, we'll just be wasting IP addresses, right? It's a way to conserve, subnetting is a way to conserve IP space. And I'm getting a little ahead of myself into some of the later chapters, but one of the primary uses we will be using it for this conversion is to subnet, right? To be able to segregate accounting, a group of people that should be in accounting workstations from HR workstations, from workstations in a remote location or a satellite office, right? All these different subnets help us in terms of access control, providing permissions, how things are routed and switched. So it provides management and security, being able to subnet. But we'll go ahead and continue on. So converting between binary and decimal numbers, there's a video if anyone wants to watch this, feel free to, but I'm just going to continue to discuss. Now, binary and positional notation. Something that we really need to understand is that in binary, the position of the bit is really important. That specific digit, that whether it's a 0 or a 1, depending on the location and position in that stream of data, it's going to change the value of that digit. So pretend if we have an octet, we have 8 positions. Okay, when we're talking about positions and numbers in general, when it comes to technology, usually we consider 0 as a number. So specifically for binary, 0 is considered a position and a number. All right, and when we're talking in binary, additionally, rather than reading left to right, which we do for decimal numbers, in binary we read right to left. Okay, and let's just say we're talking about octets. In an octet, there's 8 bits, so that means there's 8 zeros and ones to create a digit. Depending on where the zeros and ones are within that octet, those 8 bits, it's going to change the value. It's going to change the number when it gets converted to decimal. Okay, so let's talk about positions first. Like I mentioned before, there's going to be 8 positions, and 0 is considered a position. So when you see here, it usually starts at 7, and we're reading right to left. All right, so that's why you see 0, 1, 2, 3, 4, 5, 6, 7. Okay, now in these 8 positions, a 0 or a 1 could be positions, number, right? Can occupy that position. Now, whenever a number gets occupied in a specific position, then it changes the number, right? So this number is completely different than this number, because there's an additional 1 at this position 0, and it will look completely different. I'll tell you right now. Let's see, what is this? 2 plus 8, this is 10, this is 11. So the decimal number of this is 10, the decimal number of this is 11, because of this 1 bit. If it was like this, this total number, when you convert it to decimal, it's 128. All right, and we'll go into how you calculate that. Now, the way you calculate that is you take base 2, and then you use the position as a power, and you calculate that to determine what happens if all positions are a 1. Now let me go into this, let me explain. All right, so when we're talking about, let me pull this back up. So when we're talking about our positions, right, 0 through 7, you take base power 2, all right? We always use 2 because remember, there's only binary, there's only 2 different numbers that it can be. It can either be a 0 or a 1. So we use base power 2. And then we take it to the power of n equaling the position of the location of that bit. So you have to think a little bit of math right now. You take base power 2 and you look at the position of that bit, wherever that position of that bit is. You, for example, if it's the 5th position, you take it, you use it as a power. So what is 2 times 2 times 2 times 2 times 2, right? That's 32, and that's the position value, right? So in the event that all, if there's all 1s in that position, then the total is going to be 32. Now let's go into an example. All right. So we have these positions. All right. And let's say we want, let's look at this right here. Let's say 2 to the n, 2 to the 5th power. 2 to the 5th power. Because this is position 5. Let's see, 2 to the nth. Let me write this down. Nth power, which is the position. 2 to the position, 2 to the position, right? So in this case, it's 2 to the 5th. This one is 2 to the 6th. This one is 2 to the 7th. And so on. Let's make this this way, and 2 to the 4th, 2 to the 3rd, 2 to the 2nd, 2 to the 1, and then 2 to the 0. All right. So what does that mean? Let's calculate. If we calculate that, 2 to the 7th is 128. 2 to the 6th is 64. 2 to the 5th is 32. 2 to the 4th is 16. 8, 4, 2, and then 2 to the 0 is 1. All right. So if we take base power 2, the reason why we use base power 2 is because we're using binary, either 0 or 1, and we power it to the position. We'll go here. All right. And then what does that number equal to? So 2 to the 7 is 128, and so on. So what does this calculate number actually mean other than the solution to 2 to the nth? What that means is that, for example, this 32 at position 5, if the data stream of bits is all 1s, starting from position 0 all the way up to position 5, the total is going to be 32. Okay? And the last 2 octets are going to be 0. All right? So what does it mean if 2 to the 6 equals 64? That means starting from position 6 all the way down to position 0, if it's going to be all 1s, when you calculate and add up all these 1s, it will equal 64. what does it mean, for example, 2 to the 4th is 16? That means if you calculate everything from position 4 and below, position 4, 3, 2, 1, and 0, if you calculate all these ones together, it'll equal 16. All right, and the rest is going to be 0 just because we're only focusing on that specific position. That specific position, that value itself is if all the positions beneath it are all ones. All right, so this is the value. All right, this value is position 7 is considered 128. The position value of position 6 is 64. Position value of 5 is 32. Position value of 4 is 16. Position value of 3 is 8. 2 is 4. Position value of 1 is 2. Position value of 0 is 1. So maybe it's better to write it like this. Position value. Okay. Now, how do we use this? So when we want to calculate a number from decimal to binary, what we do is, let's say we take this number of 1, let's start simple, 13. All right, we want to convert the number 13 into binary. 13 is a decimal number, decimal number of 13. All right, this is just an example. If we want to convert the number 13, what we do, or any number specifically, there's a process of steps. So the first step is identify the position it for sure cannot be in. So when we say we are trying to look for the binary of 13, it can go into position 8, it can go into position 4, it can go position 2, it can go into position 1, but it cannot go into position 16 because 13 is less than 16. All right? So in that event, it's impossible for position 7, 6, 5, or 4 to be equivalent to a 1. All right? 13 gets converted, okay, into, now you have to take this 13 and you have to add these up together. So you have these 4 numbers, 8, 4, 2, and 1. All right? We have to determine which of these numbers we can add up together to get the number 13. In this case, it goes into 8, it goes into 4, 8 plus 4 is 12. We can't have 2 here because that will be 14. That will be more than 13, so that will be a 0. And then it will be a 1 right here. So when we want to convert the number 13 into the decimal number 13 into binary, this is what the binary would look like. Okay? 0, 0, 0, 0, 1, 1, 0, 1. The reason why it'll look like this is because it's 8 plus 4 plus 1. Okay? 8 plus 4 plus 1 equals 13. Oh, there we go. Equals 13. Right? We are converting that decimal number into binary. And the reason why we can't say that, and to represent this 8 plus 4 plus 1, we have to switch the bit from a 0 to a 1. That means we're turning on, yes, if we turn on 8, if we turn on position 4, if we turn on position 3, position 2, and position 0, that means we're adding 8 plus 4 plus 1 to get 13. Okay? Now, if we're talking about the number 56, let's say we want to convert the number 56. We take a look at the maximum value that 56 can actually be a part of. So because 128 is greater than 56, that'll always be a 0, right? To represent 56 in the number 56 in an octet, the position value of 7 will always be 0 because position value of 7 is 128. Same goes as position 6. The position value of 6 is 64, so it will always be a 0 if we're trying to convert decimal number of 56 into binary, right? Now, going down the row, okay, we can do 32, right? So now we subtract 56 from 32. My 32 equals, right here, let's do this. Let's do this. So we'll do equals this minus, actually, let's see, let me do this back here. All right, we'll do 56 equals this minus this. All right, so we have 24 left. So now from the last 5 positions, starting from position 4, we have to total the number of 24 with these 5 numbers. Okay. So what we can do here is now, let's say we put a position value of 1 here. So what we can do is subtract 16 from it. So now we have 8, right? Oh, 8 fits perfectly in 8 right here in position 3. So what we can do is actually just subtract that from this and equals 0. So to represent the number of 50, and the rest of the positions become 0. So to represent the number 56, it would be 0, 0, 1, 1, 1, 0, 0, 0. Okay? Now let's do one more example. Let's say we want to do the number 140. Okay? First, we take a look at which of these numbers can actually fit into 140. We see that all the numbers can actually fit into 140. So we'll start from the highest number, positional value is 128. So we'll put a 1 right there. All right? Now we subtract 140. All right? Minus the 128. We have 12 left. All right? We take a look at 12. 64 cannot go into 12, right? So position 6 would be a 0. 32 cannot go into 12, so position 5 is going to be a 0. Position 4 is 16. 16 is bigger than 12, so position 4 is going to be a 0. Now we get to position 3. 8 is smaller than 12, so we can put a 1 right here because 8 goes into 12. So what we do here now is we subtract that from position 3. Now we have 4 left. Okay? 4 goes into 4 perfectly. So we put so there is a 1 in position, there is a 1 in position 2 because 4 fits into this subtraction perfectly. And then if we do that, if we subtract 4 from it now, we have 0 left. So the rest of the positions can be 0. So the binary conversion of the number 140 to decimal is 1, 0, 0, 0, 1, 1, 1. Sorry, 100011100. Now, if you add all the positional values together, if you add 8 plus 4 plus 128, it'll give you 140. All right. Now, what if we do it the other way around? All right. So let's go ahead and erase this real quick. Delete. What if we have a decimal number and we want to convert it into what if we have a binary number and we want to convert it into decimal? So let's say we have this number. Oops. We have 8 bits of zeros and ones. What would this number equal to in decimal? Decimal, all right. What we would do is we would add up the positional value of all the ones, so to get the decimal number. So what that would be is this equals all the positional values of 1. So it'll be 64 because position 6 is 64 and there's a 1 there. And then we add position 5, which is 32. We add position 3. We add position 2. We add position 1. And we add position 0. Okay? Now, we are adding all the values that have a 1 in their position. We press enter. This number, the value of it in decimal is 111. Because we added up all the ones in the positional values together. All right, so 1 plus 2 plus 4 plus 8 plus 32 plus 64. All right, so that's how you go from decimal to binary and binary to decimal. Okay, so let's go ahead and continue on. This lesson specifically, it gives a few additional examples. For example, you'll see here converting an octet of this binary number into decimal. Just like we did here, we find the positional values, we write the binary number, okay, and then you just add them all up together, right? In this instance, if we have this number of 1010100, we're adding 128 plus 32 plus 8. You see here 128 plus 32 plus 8 equals 168, all right? And then within the rest of the module, it's just examples and practice activities to go through. Okay. Let's see. So, for example, let's say, let's see. Let's see. Okay. Now, let's see how this relates back to these binary into IPv4 addresses. Remember how I said that every IPv4 address is an 4 octets, 32 bits? So what we see as an IPv4 address is the decimal version, right? We see 4 numbers separated by decimals. So 192.168.10.10. If we convert that, I don't know if it shows here, yeah. If we convert that into 4 different octets and we write them binary, you'll see that the actual value of 192.168.10.10 will look like this. So 32-bit, it will look like this. Okay? All right. Now let's jump into hexadecimal. Hexadecimal, we're going to go briefly over it. We're not going to dive too much into it just because for the most part, we will be focusing on IPv4 within the CCNA Networking Fundamentals beginning course. but it's good to just have a general understanding of what it is and just how to convert. It's relatively similar in terms of the conversion. So in decimal, we have the regular number system, right? 0, 1, 2, 3, 4, 5, 6, 7. In binary, we have zeros and ones. In hexadecimal, we have 0 through 9, A through F. So 16 characters that can represent one digit. Okay? So what that means is that if there's 16 numbers or 16 different characters, if we're trying to convert a hexadecimal into binary, we'll go back here in our Excel document. There's 16 different combinations of zeros and ones you can do all the way up to positional 3, right? So I kind of brought this down here. I copied and pasted it, right? You can either have all zeros, 3 zeros and a 1, 0, 0, 1, 0, 0, 0, 1, 1, 0, 1, 0, 0. So I'm not going to go through all of them, but essentially there's 16 different combinations you can have for zeros and ones. All right. Now each of these combinations will represent a different hexadecimal character. The hexadecimal character, I believe it's just, it's 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. All right. Each of these permutations equal a hexadecimal value, right? 0, 0, 1, 1 equals 3. 1, 0, 1, 1 equals the letter B. All right. Now in hexadecimal, each of these represents one bit. All right. And also something to notate is that in hexadecimal, capitalization versus lowercase capital doesn't matter. The letter is what matters. It doesn't matter if it's capital or not. But essentially, each bit is represented by one of those 16 characters. And if you convert it to binary, it goes all the way to position 3 because there's 16 permutations of zeros and ones. Okay. Now, the only reason why we use hexadecimal necessarily, well, there's 2 reasons. One, MAC addresses, but specifically from the network layer perspective, we use hexadecimal for IPv6 specifically because binary, when we're talking about binary, IPv4 uses binary 32 bits. 32 bits only has a limited number of set IP addresses because we take a look at binary 0 or 1, base power 2, and then we power it to the 32nd power. When we do that, we have, I think, was it 4 billion IP addresses? But weirdly, that 4 billion IP addresses is being consumed way too fast. So something that we had to do, some of these frameworks, IEEE and some of these other standardized frameworks, is they created IPv6 to mitigate the risk of running out of IP addresses. So now we use IPv6, which has IPv6 is 128 bits, right? So we do 16 times 128, and that's a lot more IP addresses that we can utilize, rather than 4 billion, which is 2 to the 32nd. Anyways, those are the 2 reasons, MAC addresses and IPv6, why we even think about hexadecimal. Okay, and from a hexadecimal standpoint, it's relatively similar in terms of how you want to convert. So the only difference is if we pull up our Excel sheet again, right here. Now, if we wanted to convert this 111 into hexadecimal, what we would do, remember hexadecimal is 16, so every 16. So that's 4 bits. So what we would do is we would actually split this up. We'll do yellow, and then this is like, let's just say another color, orange. So this would be the first part of the hexadecimal, and then this would be the second part of the hexadecimal. So if we want to convert 111 to hexadecimal, what it would look like is, all right, 0110. What would that equal to? I have this chart right here that I created. 0110, so that's 6, all right? And then 111 is F, all right? So the hexadecimal of 111, or this string of numbers, is 6F. Because what we do is we take a look at only 4 bits at a time during hexadecimal, and we have a map or some type of chart that maps out, and this is always going to be standardized, right? Whenever you're doing hexadecimal, if it's all zeros in binary, it's going to equal to 0 in hexadecimal. If it's 0111, it's going to be 7 in hexadecimal. If it's 1101, it's going to be D in hexadecimal, right? So this kind of like chart is relatively mapped out and standardized. It doesn't change. So we take a look when we're converting binary into hexadecimal, we look at 4 bits at a time. So we take a look, all right, 1111, all right, let's see, it's F. All right, so it's, and then we take a look at this, 0111, 110, it's 6. All right, so it's 6F. And when you're converting, you start with the first half, you start left to right. So first half and then second half, which is F. And then first half, and then which is 6. All right. First 4 bits, we can do second 4 bits. All right. So that's pretty much how you convert binary to hexadecimal. Okay. Let's go on, continue, and then I think there's just another example down here. And some questions. So that kind of wraps up numbering systems. Let me know if you have any questions. Remember, binary and hexadecimal are really important just to understand from an addressing perspective. And yeah, this is like very, very basic foundation. We haven't got into subnetting, but once you get a good foundation of conversion of binary, then subnetting is going to be a lot easier, right? If you understand binary, subnetting is going to click immediately. All right. Anyways, that wraps up this module. Let me know if you have any questions, and I'll see everyone next time. Thanks.